Hello everyone, this is Georgios Kasparis from Software Competence Center, Hagenberg, and I'm presenting a paper on generalized input-output hidden Markov models for supervising industrial processes. This is a joint work with my colleagues Sabrina Luftensteiner and Michael Mail. Often in industrial processes, batches of material are processed sequentially through several process steps. And these process steps may or may not be identical. There is a large number now of sensor measurements collected in each part of the process, and this amount of sensor data is continuously increasing due to the digitization of industrial processes. So this creates a rather increased complexity with respect to the data analysis required when we, let's say, try to identify, detect operating conditions, for example, abnormal behavior. Input-output hidden Markov models can provide a framework for detecting operating conditions. However, they are based on an underlying assumption that there is an identical process. This process repeats continuously. However, let's say the physical laws, the underlying physical laws of this process, or the details of this process remains identical. However, industrial process may comprise several non-identical steps that do not, let's say, are not based on the same laws, or they have different kind of phenomena that take place. To this end, we need a generalized version of input-output hidden Markov models in order to use such a framework in the context of industrial processes. In this figure, we see a schematic of a potential manufacturing line, which is assumed to be linear. In other words, we assume that the number of steps is going to be predefined and fixed. And in each of these steps now, we have several parameters, properties characterizing it. In particular, we have the material property specifications I. So these are parameters related to the batch item that's going to be processed. We have configurations or inputs U. This could be, for example, some parameters manually defined by the machine operator. We have sensor measurements collected periodically. And finally, we have states or operating modes X that we artificially assign to each of these steps because we try to characterize, let's say, the conditions under which this step currently operates on. And the main question here is what is X? As I said, X is a kind of artificially introduced in order to capture different regions of operations that we can, let's say, observe through the sensor measurement. Let's maybe consider a toy example where we have one sensor measurement, which is the energy consumption at a particular step. And this energy consumption takes either a high value or a low value. In this case, and assuming that this is the only two values that energy consumption can take, essentially it's sufficient that we consider introducing two operating modes, X1 and X2. And X1 is, let's say, matches the operation at the low energy consumption, and X2 matches the operation, corresponds to the operation at the highest energy consumption. So in principle, here we would like to develop methods with which we can infer with respect to the current operating mode. And at the second step, we would like to also create predictions over the states in the upcoming steps. Because in this case, we would like to be able to predict, let's say, certain deviations in the operating modes that are non-desirable, which also can potentially be avoided by selecting the appropriate control inputs U. As we discussed in the previous slide, the objective here is to be able to infer over the operating conditions in each of these given steps of the process. And by following such inference-based approach to process diagnostics, we indirectly manage to classify over the operating conditions. And this is done essentially indirectly by the methodology, let's say in the hidden Markov models, through splitting essentially the feature space of the sensor measurements into different regions, each of which corresponds to different operating states. Through such a process, also we manage the dimensionality reduction of the original feature space. Instead of working directly with the possibly very large feature space of the observations, we work instead in the state space, which is significantly reduced. Third, we can generate predictions over upcoming operating conditions, and this is usually achieved, especially in hidden Markov models, through the structure that is indirectly introduced into the system, meaning the states of a given step would depend on the states of the previous step, and this introduced, let's say, Markovian property has a significant advantage in generating predictions over the upcoming the upcoming steps. And finally, which is a kind of also related to the structure introduced by the Markov property, we have the opportunity to provide state-based optimization. So instead of optimizing with respect to, let's say, the control inputs based on the whole feature, the whole observation vector that we observe, we can optimize with respect to the state that the current step is currently operating on. So again, this dimensionality reduction is beneficial not only for generating predictions and diagnostic, but also for optimization. In the remaining slides of this presentation, I'm going to briefly discuss the related work and contributions of this paper, and then we're going to discuss the standard form of input-output hidden Markov models, and then the challenges related to describing linear process lines, industrial process lines, and how generalized input-output hidden Markov models can help us actually model these linear process lines. Finally, the paper describes the training of such generalized input-output hidden Markov models. However, in this presentation, we're going to skip the details of such training algorithm. Starting with the related work, we should mention that hidden Markov models and input-output hidden Markov models have been used extensively to generate diagnostics, predictions, as well as optimization, and also in different kind of use cases. For example, in the domain of electricity prices, in providing and assessing the system health, or motion patterns in dynamic objects. The reason, and actually this is worth mentioning, the reason for considering hidden Markov models based, let's say, diagnostics here is because of the convenient structure that is introduced into the system that has multiple advantages with respect to how we generate predictions over time in the upcoming, let's say, process steps, but also in the future, in case we would like to optimize that the process, this Markov property is actually quite handy in providing even closed form solutions in several of these optimization problems, or for providing, let's say, the basis for reinforcement learning approaches, for example. So far, there has been limited work on applying hidden Markov models or input-output hidden Markov models on industrial process lines, and the reason of that is primarily related to the fact that standard input-output hidden markup models are not directly applicable to industrial process lines when we have multiple steps that are non-identical. So the main contribution of this paper is to introduce a generalized version of input-output hidden Markov models, which is specifically tailored for industrial process lines of multiple non-identical steps. Now, this methodology would allow for diagnosing over operating conditions for each step independently and considers temporal dependencies in two, let's say, orthogonal dimensions. In particular, we consider temporal dependencies among steps that are sequential steps when processing the same batch item. So once the state or the operating mode of one step influences the operating mode of the next step as the same batch item is processed. And the second dimension of, let's say, such temporal dependencies is over steps over the same step when processing different batches. So, for example, when we process currently one batch in process step 1, this would be influenced by the operating mode of the same step, step 1, when processing the previous batch. Finally, we present a methodology that trains such input-output, generalized input-output hidden Markov models using time series data, and we provide actually the proposition and the analytical actually framework to that demonstrate that the proposed training is actually at least suboptimal. So, in fact, the model always improves with respect to the capturing the observed time series data. The following figure shows a standard input-output hidden Markov model, which comprises sequential steps of an identical process. So this process repeats, the same process repeats every time interval t. And at each of these steps, we have a certain set of control inputs u, whose values might change over time, but the set of control inputs is always the same. And we observe a set of observations y, the values of which also might change with time. Now, each of these steps is characterized by a state variable. The set of the state variables here is assumed the same for each of these steps. Simply the values changes over time. When addressing the problem of diagnostics in manufacturing process line, which is here is assumed to be linear, the conditions are slightly different compared to the standard input-output hidden Markov models. The reason lies primarily to the fact that the different process steps may not be identical, meaning the underlying physical processes are different compared to the between steps. At the same time, there are temporal dependencies between sequential steps. The operating mode in step 1 is probably going to influence the operating mode in step 2. At the same time, there's also dependencies between batches, meaning the operating mode in step 2 when processing batch B+1, as is the case here, is going to be also influenced by the operating mode of the same step when processing the previous batch. This schematically is shown in this figure, where we have plotted by arrows the temporal dependencies considered in this analysis. As I said before, there are temporal dependencies between operating modes of sequential steps, as well as between the same step when processing different batches. It's important to mention here that there's two important underlying assumptions that have been considered in the analysis of this paper. And the first one is about the Markov property between process steps and between batches. In particular, and as we mentioned in the previous slides, we have assumed that the operating mode in one of the steps, let's say in the step 2, will be influenced by the operating mode in the previous step, as well as of the operating mode of the same step when processing the previous batch. So in principle, we have assumed this Markov property between process steps and between batches. However, it's important to note that the same analysis can be extended in a straightforward manner in cases this dependencies is of higher order. In case, for example, there are dependencies that go beyond one step ago. In this case, there's actually a standard trick that we can employ where these higher order dependencies can be translated into one-step dependencies by simply extending the dimension of the state vector. At the same time, we also assume here that the sensor measurements follow some Gaussian distribution, and the parameters of this Gaussian distribution is also subject to the training of this hidden Markov input-output hidden Markov model. The details of training such a generalized input-output hidden Markov models are described in detail in the paper. Here we just mention the categories of the parameters considered in this training process. First of all, there's parameters associated with the state transitions. For example, when there is a given state in step 1 when processing batch p plus 1, and there's also a given state in step 2 when processing batch p, then this combination of these two states may have different possible transitions to the state of step 2 when processing batch p plus 1. And all these possibilities, let's say, of transitions should be parameterized, and the parameters of these transitions is subject to training. At the same time, the statistics of the Gaussian distribution, the mean and the variance of these Gaussian distributions of the sensor measurements is also subject to training. So in the paper, there is analytical derivations of these recursions for updating these parameters, and we saw, in fact, that the training leads to suboptimal updates, meaning that the likelihood with which the data is captured by the proposed model is actually increases. In conclusion, in this paper, we presented a generalization of input-output hidden Markov models that is more appropriate for manufacturing process lines. And an interesting aspect of this work was these temporal dependencies that extend over multiple dimensions. In particular, we have temporal dependence between process steps when processing the same batch, but also we have dependencies between steps when processing different batches. In the paper, we present a framework for training such a input-output hidden Markov model, and an extension to higher order, let's say, of temporal dependencies is also possible. However, it requires an extension of the presented analysis. As a future work, we intend to run tests in real-world manufacturing process lines for providing diagnostics as well as predictions over the operating modes of these different steps of the process. And also we plan to incorporate such a modeling framework into an optimization framework that intends to provide suggestions to the operators in different process steps with respect to certain performance indicators. Thank you very much for your attendance.